welcome back. Let's put this alpha to work and get a formula here. Actually, formulas. So, for formulas for constructing a 1 minus alpha times 100% confidence interval, the lower bound is your point estimate minus z sub alpha over 2 times the square root of the point estimate times 1 minus the point estimate over n. Don't worry, we're going to do an example, so you'll see how this all goes together. The upper bound, oh, and those words remind me that I meant to, let's just step back a minute so that we actually know what those words mean. So back to the first page of the 9.1 notes. Okay, here, I meant to tell you those words. So remember, we came up with this confidence interval based on what the Gallup organization information was. The left-hand endpoint of the confidence interval is called the lower bound. And so what I just read to you was the formula for getting that. And so this is some formula that probably the Gallup organization used. They don't share that with you, but this is how we're now going to learn to construct, to do what the Gallup organization did here. This number that marks the right-hand endpoint of the confidence interval, you might have guessed, is called the upper bound. Okay, so when I'm giving you formulas to find the confidence interval, what you need, of course, is where it starts and where it ends. And that's what these formulas are for, the lower bound and the upper bound. Okay, so back to the formulas. Here we go. The upper bound is your point estimate plus the same thing up there. In other words, so notice that you've got your point estimate, and then you've got a certain distance above it and a certain distance below it. The Gallup organization computed that distance above and below to be 4% or 0.04. That's called the margin of error. That's why they called it that. So what I actually kind of prefer in terms of a formula is just to know that the formula for the margin of error, E, is z sub alpha over 2 times that square root. And then I know that I'm going to go E above the point estimate and E units below the point estimate. So another way to look at this is the lower bound. The lower bound, and you want to know this principle. The lower bound is the point estimate plus the margin of error, minus the margin of error. I hate not being able to use pencil. And the upper bound is the point estimate plus the margin of error. Okay, so I don't consider these formulas that I would need to give you. I'm going to assume that you know that to make a confidence interval, you center it on the point estimate, and then you go up and down, left and right, down and up, both sides of that point estimate. So as long as you know that, you only need to use the formula for the margin of error, and all these lower bound and upper bound formulas are saying, you're going to go down that margin of error from the point estimate, up the margin of error from the point estimate. Okay, let's see an example. So 800 randomly sampled teenagers were asked whether they have ever texted while they were driving. Of the 800 teenagers surveyed, 272 indicated they had texted while driving. So we're going to obtain a point estimate, p hat, for the proportion of the teenage population that has texted while driving. So we'd like to know the proportion of the teenage population that's done this. We can't possibly ask every teenager the question, so we're instead going to ask 800 of them, and the proportion of the 800 that answers the yes to the question, that's going to be our estimate for the proportion, our point estimate, for the proportion of teenage population that has texted while driving. And then, as we've seen, we don't want just a point estimate. We want an interval so that we can express a level of confidence in our estimate. So we'll obtain a 95% confidence interval for the proportion of teenagers who have texted while driving. And then we will also look at what happens if, instead of going for a 95% confidence level, if we go for a 99% confidence level. What is that going to do to the margin of error if we go to a higher confidence level? Okay, so here we go. First of all, I need the point estimate. Okay, so the point estimate for the proportion is the number of successes, the number of people that said yes, divided by the size of the sample. And we were just told that 272 said yes, I have texted while driving, out of the 800 sampled. And if you do that on a calculator, you'll get 0.34, or about 34%. Now, in our formulas, let me grab that margin of error formula again. So in our formula, we're going to need to know n, that's the sample size, that'll be 800 in this case. We need to know p hat, our point estimate, we just figured that out. Now I also need alpha, and from alpha I need to, notice the formula is actually uses alpha over 2, so I'm going to calculate alpha, divide it in half, and then I have to find the z sub alpha over 2. So I'm going to do some calculation using formulas, and then I'm going to go to the standard normal distribution table to come up with that z. Okay, so that's where we're headed. So that's why the next thing I need to do is come up with alpha. So remember, alpha is 1 minus the confidence level as a percent, and we desire 95% confidence level, so I'm sorry, confidence level is a decimal. So we desire 95%, so I'm going to write 0.95. So alpha is going to be 0.05. Now that means then, this arrow with this double arrow, by the way, is math shorthand for the word implies. It doesn't mean here's my answer or these two things are equal. It means this fact implies the next fact. Anyway, that implies that alpha over 2 is 0.025. And so the z that I'm looking for to put in the formula, z sub alpha over 2, is z sub 0.025. Okay, so I'm going to look at the table now to get the z, but let's think about how that's table 5 in the back of the book. Let's remind ourselves how that works. The table tells you the z with the area to the left. So, I mean, what I want, say this area is 0.025. So I want this number, z sub 0.025. Because z sub alpha means the z that has that area to the right. The problem is the table gives you the z value for the area to the left. So there's a couple of ways of dealing with that. I remember the total area under here is 1, so I could say, well, if the area over here is 0.025, then the area here is 1 minus 0.025. And look for the z. So what would that be? So 1 minus 0.025 would be 0.975. So I could look for 0.975 in the table to get this z value, because again the table is based on area to the left. But there's what I think is an easier way of doing this that involves fewer calculations and fewer numbers being thrown around, and that is to remember that for the standard normal, and remember when you're looking up stuff with z's on that table, you're talking about the standard normal. So remember, the standard normal is centered at 0 and it's symmetric. Unlike my hand-drawn version here, it's symmetric, it's not lopsided. So the if I use the table to get the z value that has that area to the left of it, okay, I'm going to get is actually the opposite of this z-value, 0.025. Okay, so I'm going to get the opposite of the exact number I want. I'm going to get the number I want with the minus sign on it. So the easiest thing to do, I think, is to just go ahead and look for 0.025 area in the table, then recognizing that what the table is giving us is this number, not that one, but that they're the same with a change of minus sign. I'm just going to get this one and throw away the minus sign. Okay, so with that explanation, going over the table, so remember the table with the positive z values are where the z's are to the right of 0. They're to the right of the middle. So I'm going to want this table. Remember, these numbers give me the area. I have the area. I want the z. So I know that the area I want here is 0.025. So I look in here for that. Let's see, 0.025, 0.025. There's 0.026, there, 0.025. Okay, so the z-value that goes along with that is minus 1.96. So the number I want is 1.96. Right, the table gave me the minus 1.96. What I actually want is the 1.96. Again, why? Because this notation just works the opposite way from the table. This notation is indicating the z with this much area to the right. The table, though, always looks for areas to the left. Okay, so so again, we get 1.96 here. So our margin of error, we're going to plug into that formula z sub alpha over 2 times the square root of the point estimate times 1 minus the point estimate over the sample size. So for us, for this problem, that is 1.96 square root of, our point estimate was 0.34 times 1 minus 0.34 over sample size was 800. Okay, and then obviously you're just going to crunch those numbers on a calculator, and in this case we'll get 0.033. Okay, so for our confidence interval now, the lower bound, remember the lower bound is the point estimate minus the margin of error. So that's our 0.34 minus 0.033, which works out to be 0.307. The upper bound is the point estimate plus the margin of error. So in this case, that's 0.34 plus 0.033, which works out to be 0.373. Okay, so our confidence interval goes from 0.307 to 0.373. What does that mean? Let's write down an interpretation of that. Summarize all this stuff in words. So interpretation of what we've just done, we are 95% confident with that weird definition of confidence. We are 95% confident that the proportion of teenagers who have texted while driving is between 0.307 and 0.373. In other words, between 30.7% and 37.3%. Okay, with 95% confidence. Again, remember, that does not mean that there's a 95% probability that the actual proportion is between these two numbers. What it means is that if we used this same method of setting up the confidence interval, then 95% of the time the confidence interval is going to contain the true proportion. That's what 95% confidence means. So that's probably a good stopping point. We've got a little more to do with this one, but I'm going to stop the video here and we'll come back and keep working in the next one.